Hello, students. So we will work on finishing off reaction rates by looking at reaction mechanisms. This will not be nearly as long a video, but it may still be a challenging video. Less math, but more thinking, so bear with me. So, reaction mechanisms is the last thing we can talk about. This is what relates the math portion with the molecularity of what is actually occurring. Now, when we look at the overall balanced equation, that balanced equation just gives us a general picture of what has to happen. The idea that atom A and atom B have to collide, or that atom B and atom A are converted into molecule C. But that doesn't always show us what needs to occur. So looking at a general reaction of destruction of ozone by monatomic oxygen, that the reaction is that O plus O3 forms 2 molecules of O2. This is a destructive mechanism that happens when that happens occasionally over time, but this process is normally incredibly slow. Ozone does not usually decay by this mechanism. However, if we add certain catalysts to the reaction, this will greatly speed up. That the CFCs, chlorofluorocarbons, or NOx gas can speed this up, make the decomposition quite noticeable. Now, based on the overall reaction, you would expect that, ozone is first order and oxygen, monatomic oxygen, is first order. Those two must bump into each other. Which that is kind of the case in the uncatalyzed reaction. But when these pollutants are present, these catalytic pollutants are present, that is not the situation. We see that ozone is the first order, but oxygen is not. So the overall reaction can be split into 2 separate elementary reactions that when you add up the elementary reactions, they add up to the overall equation. When you say an elementary reaction, you're saying a reaction that cannot be simplified any further, that it shows the literal collisions that must be occurring to move to the next step. So, with that in mind, these elementary equations will provide the reaction mechanism that we see what is happening. So in this equation, we see NO collides into ozone to form NO2 and 1 oxygen. Then the NO2 can hang around until it bumps into a molecular oxygen, at which point it reforms and you get a second oxygen atom. If you add those up, we have 1 NO2 on the left and 1 NO2 on the right. They cancel out. We have 1 NO on the left and 1 NO on the right. They cancel out. But O and O3 stay behind and 2 O2s stay behind. Similarly, chlorofluorocarbons can break apart to form CO radical. That will form ClO radical, and the ClO can then reform the Cl radical. In this case, the NO2 and the ClO radical are intermediates. They are products that don't appear in the overall reaction because they are consumed as a reactant in a later elementary step. That they can be captured, they can be isolated. They are not transition states. They can be isolated. But if you allow nature to take its course, they will not remain behind. Because takes place in 2 steps, each step has its own relative speed. And because each step has its own relative speed, there must always be a step that is considered the slow step. This step is called the rate determining step. I previously described building houses. If the painting is not the slow step, the framing of the house is the slow step, how many houses you can build depends on how long it takes to frame a house. The same way that that reactants, however many times you can react, depends upon the slow step. Everything that is in the slow step is going to control the reaction. Everything outside of the slow step is not going to control the reaction. If a house takes a couple hours to paint, regardless of how many painters you have, then the amount of painters is going to speed up the house building process. But if the time it takes to frame a house depends on how many framers you can get, well, then more framers means faster houses being built. So when we write the rate law, each elementary reaction step can be written so that the rate law is directly based on that elementary reaction equation. So for that 2-step reaction, the rate of step 1 would be equal to the K1 times NO times O3. That NO and O3 bump into each other and react. Rate 2 is based on K2, where NO2 and O collide. This is the only time the coefficients are equal to the reaction order in these elementary reaction steps. But to determine the elementary reaction, we need to study the data first. Now, for that reason, reactions with termolecular overall reaction order are very unlikely. They're not very common because the likelihood of 3 atoms colliding simultaneously with the correct orientation and the enough energy is highly unlikely. 2 atoms colliding, that's easy. 3 gets a little bit trickier. 4, it's even harder still. So now each elementary step has its own rate constant. Each reaction mechanism, 1 step will always be the rate determining step. But in terms of this reaction above, K1 has a rate constant of 3.5 times 10 to the negative 15th. K2 is 9.3 times 10 to the negative 12th. So, that in mind, that the first reaction is about almost like several thousand times slower than the second reaction. So even though they're both very slow, step 2 is fast, relatively speaking. So step 1 would be considered the slow step. So the rate determining step always controls the speed. It is the bottleneck of the reaction. What that means is, like in a 2-step reaction, every time an NO2 forms, it is almost instantly consumed and it regenerates the NO again. So by the time the second atom of NO2 can be formed, the first NO2 has already gone. And if the bottleneck occurs early, we ignore all of the later steps from the overall rate law. Because the first step is the rate determining step, we get a reaction rate law that just says constant K times NO times O3. Now, because NO is regenerated, and so it doesn't really change in concentration, it can be actually absorbed into the K constant. And so we can just get a rate that is simply first order with respect with O3, but zero order with respect with molecular oxygen, meaning the amount of molecular oxygen does not speed up or slow down our reaction. But one thing to note, regardless of what reaction mechanism you may try to determine, it should match with the overall rate law that we found experimentally. The mechanism is the hypothetical, it's the hypothesis that needs to be backed up by the experimental rate law. So, if the first step is slow, this is what we kind of see. So, generic reaction where A, B goes to C, and then C reacts with D to form our product E. With a slow first step, we only see a direct relationship of A and B together. So that every time a C forms, it gets used up. It has no time to build up to any sort of concentration. So the reaction completes, and the concentration of D will not affect the reaction rate unless D is so small that it bottlenecks it in a different way. Now, if the second step is slow, things can get a little bit trickier. In a slower second step, so like as we'll see in the next chapter, when we have reversible reactions, that A and B rapidly react to form C, but some of the C decomposes to form A and B, the amount of C present is controlled by the amount of A and B we started with. And so we have a comparative amount of C based on A and B. If we're bottlenecked where the C then has to bump into a D, our equation is essentially going to be in terms of the initial concentrations of A, B, and D. It's a little trickier. Because the slow step, since the step of 2 is slow, we have a chance to build up C, but C cannot be directly measured. Because we cannot directly measure C, we did not put C in there, we put A and B. So we have to find C in terms of their concentrations from A and B. So with that in mind, we can set, if this is equilibrium, we can set the two of them equal or related and substitute for C, and that's how we get A and B times D. So if the second step is slow, basically the rate will depend on both steps rather than just simply the slow second step or the slow first step. That the amount of A and B there is going to control how much C we have and thus how fast step 2 can go. Now, I want you to try to match the rates with these reactions. The easy ones are the ones where it is the first step is a slow step. In the rate determining step being the first one, A and A react to form C, and C reacts with B to go to D. Now, A and A goes to C, so it's second order with respect with A, but since B is in the second step, we ignore B entirely. So, example number 2, rate is Ka squared, matches our first reaction mechanism. Now a different reaction mechanism where A and B react to form C, but then C reacts with another A molecule to form D. In this case, the first step is still slow, but now it's a first order with A and a first order with B. So that's example C. And then if the second step is slow, A and A react to form C, but then C reacts to form B. So we have to replace C with the A squared. And so we have an order dependence. So A plus B. So example A matches up with the mechanism of 3. So these are 3 reactions that each have the same overall equation, but they would each have 3 different rate laws. So depending on the data that we would manage to recover depends on which of these mechanisms would most closely resemble what is actually occurring. Now, so here's an example. Propose a 2-step mechanism that might fit this data. So 2 NO2s plus F2 goes to 2N2OF. So 2 of these guys, and it's a direct first order with NO2F. So there's several different ones, but basically there's 3 molecules that need to react, but the rate determining step has only 2 of the molecules. So looking at this, quick. NO2, 2 of these, and F2 goes to 2NO2F. We don't have to know exactly what's going on, just that the idea that the rate determining step is NO2 and F2. The mechanism is probably something like this. You form one equivalent of NO2F and F. That's probably the simplest thing. And then the NO2 then collides with the F, and this is fast, and this is slow. It takes a lot of energy to break the F, but then that F wants to react, and so it bumps into another thing and reacts right away. That's a likely mechanism that you could see based on the fact that the rate law of this would be rate is equal to K NO2 and F2. And the rate of this one would be rate K NO2 and then F intermediate. So first order. So this is just hypothetical. If we manage to capture an F atom, well then we know it's this. But you need to first kind of tease it out with the data first. Now, to end things up, we're going to talk about catalysts. What do catalysts do? Well, catalysts greatly speed up our reactions without being consumed. Now, how does this happen? They work typically by creating an alternative mechanism that has a lower activation energy. So oftentimes we turn a one-step mechanism into a two-step mechanism. So forming some sort of intermediate. The key thing here is they have the same starting point, the same ending point. Same products, same reactants. So because the catalyst is consumed in the first step but regenerated in the second step, very little catalyst is actually ever needed. You just need enough to start it going. Because we have a lower activation energy barrier, it's a lot easier to go to products than it is to try to go by itself. Now, enzymes is a perfect example. It grabs onto an atom and holds it in such a way that these two molecules can react, or this bond is now vulnerable and easier to break. Heterogeneous catalysts, things that bind onto other things, make it easier for molecules to interact. Hold them in just the right way that we can keep adding in a way that this wouldn't have done otherwise. But so catalysts, rather simple, but essentially changes the mechanism. Now, one further practice, propose a mechanism for the decomposition of hydrogen peroxide by iodide. So 2 hydrogen peroxides break down to H2O and iO2, and the mechanism is just first order with H2O2 and I. This is our last slide. So all we have to do is we have to find a rate. What we have to propose a hypothetical mechanism that has H2O2 and I minus. It doesn't have to be perfect. It doesn't have to be right. It's just a hypothetical. And since we want to get to H2O2 and O2, maybe it looks like this. I'm just spitballing. I minus. Maybe it forms IO minus and H2O. We need to form two of these guys. So the second step would be then H2O2 and IO minus react to form H2O and O2 and I minus again. That's just hypothetical. I don't know what it is. I can't remember if I ever did. But that's just a hypothetical situation where if this is the rate determining step, that this is the slow step, then that would fit the data. That H2O2 can react with another H2O2 molecule to break apart, but because this I minus is in there, it maybe speeds this process up. And so that's where we'll stop. I want you to have a good day, and we'll continue Chapter 15 at a later date.